and welcome to the walkthrough for the sequences work on further maths. So a lot of this is built upon the work that you did with Mr. Standen, plus a little bit of extra. We did talk about limiting sequences and stuff like that, or limits of sequences. So hopefully it's nice and straightforward. As always, feel free to skip to the end if you just want the answers. Okay. It looks like a rubber, even though it's a pen. That's useless, isn't it? Right, so a linear sequence starts, blah blah blah, which term is the first term to be negative. So it's linear, so just go about our business the normal way. So it's -4 each time, so it's a -4n sequence. The -4 times stable starts at -4, so we have to add 254 back on to start ours off at 250. So which term is the first to be negative? So what value of n would be the first one to return a negative value? So when is this less than 0? Okay, so then we end up with 254 must be less than 4n. If I add that to the right hand side, and then if I divide by 4, I'll get my value for n, which is 63.5. So n is a term, it's a position, so it's an integer value, or in fact a natural number, something positive. So we want n to be greater than 63.5, so it will be the 64th term, which leads to the first negative value. And if you're ever unsure as to how to interpret this ballpark figure, try 63, try 64, see which one of those gives you a negative value. Okay. So for question 2, work out the nth term of a quadratic sequence. Throughout this video I'm going to stick to the ABC method for this. So we know that if this is a quadratic sequence, the sequence will look like an squared plus bn plus c, something to that effect. Okay, it might be that b or c are 0, as it turns out. If we think back to why this was an effective method to use, it can be used when we don't have consecutive terms, although we do in this case. The other thing I would say is if you can quickly spot what the answer is, if you compare this to n squared and you spot what the sequence is, then you can write the answer down. Okay, so we will say then, so for the first, second and third term, so when n is 1, so we pop it into our expected answer here for the nth term rule, Tn. So when n is 1, we get a plus b plus c equals 8. When n is 2, the expected answer is 9. So we'd have 2 squared times a, so 4a, you might remember these now, plus 2b, because that's 2 times n, plus c equals 9. And then finally, we'd end up with third term, so when n is 3, so we end up with 9a plus 3b plus c equals 14. Okay, and then we're going to call these equations 1, 2, and 3, and then we're going to use them to eliminate a, b's, and c's to find them. Okay, so we'll start by doing equation 2, take away equation 1. So we're going to end up with 3a plus b equals 1. Okay, so 4a take away a is 3a, 2b take away b, and c take away c is nothing, 9 take away is 1. And then we do 3 take away 2, which gives us 5a plus that single b term again, c's again cancel, equal 5. And then we'll take these away from each other, so we get 2a equals 4. There we go, so that take away that's 2a, b take away b is nothing, and therefore a equals 2. Working it backwards, if a is 2, then we'd end up with, using this equation here, 3 times 2 is 6, so b would be -5. And then going right back to the start, we've got 2 minus 5, which is -3. We'd have to add back on 11 to get up to 8, so c is 11, and therefore we have our nth term rule, 2n squared minus 5n plus 11. Okay, and then once you've got your answer, just take a value, like use the 23 here, put n equals 4 into this, and make sure that's the right answer. Might not be, might have got it wrong. Show the nth term for this sequence is n squared plus 3n. Now, given it's 1n squared, I'm just going to quickly jump to the other method. So we know it's an n squared, so let's compare these two. So let's put the term number here. Let's write down, so that's n. Let's write down what n squared would be, so 1, 4, 9, and 16. And let's do a comparison. So we're at n squared. What do we need? We need to, in this instance, add 3 to get from 1 to 4, add 6, add 9, and add 12. And then this expression here, is this term of differences that we need, can be described as, in fact, 3n. Okay, so there's n squared and there's 3n. So we can see that to move from n squared is 1, add 3, and we get 4. And then 4 add 6 is 10, etc., which is 3n. So that implies that our sequence is n squared plus 3n. Okay. Hence, write down the nth terms. Just going to do a quick comparison here of these ones. So this is 5, 11, 19, and 29. So that's 1 more than each of these terms here. So that's going to be n squared plus 3n plus 1. And then we can see in this case it's 1 more for the first term, 2 more for the next term, 3 more for the third term, and 4 more for the fifth term. So we have to add 1, add 2, add 3, and add 4. Of course, we can describe this addition itself as the rule n. So in fact, we just need to add another n to the sequence we already generated, the 4, 10, 18, and 28. So in fact, this must be n squared plus 4n. I really hope the pointer's working. I was doing a lot of pointing and it's not picking it out. Okay, so on to question 4. Just realised the microphone is all working here, so I'll start the audio quality. There we go, it's decent. Right, so it asks us to write down the nth term for this linear sequence. So as we can see, it goes up in 3s, but the 3 times table starts from 3, and this is 1 more each time, so it's just 3n plus 1. Hence, write down the nth term rule for this quadratic sequence. So we can see we're just squaring these terms here. So the nth term rule for that one must be 3n plus 1 all squared. Now for the sequence in part 4b, so show that the 30th term is equal to the product of the second and fourth term. So the 30th term, so if we call it t30 if this is tn. So I'm going to do this without actually having to calculate. So the 30th term will be 3 times 30 plus 1 squared, or 91 squared. And then the product of the second and fourth terms, so the second term is going to be 3 times 2 plus 1 all squared, times by the fourth term, which is going to be 3 times 4 plus 1 all squared. So it's going to be 6, so that's 7 squared times 13 squared, which can be written as 7 times 13 all squared, and 7 times 13 is 91. So there we go, they're equal to the same thing. Then for the next question, the pattern of the rectangles continues, show the sequence formed by the areas is given by this. So here we go, we've got 12, 20, and 30 for our numbers in our sequence there. So again, it tells us that it's an n squared rule, so I'm just going to stick with a comparison to the n squared. So we've got 1, 2, 3, and then maybe we'll have a look at the fourth one as well. So the first term is 12, and then 20, and then 30, and then if we compare that to the squared numbers, which of course are 1, 4, and 9 for these particular numbers here, that's n squared. And then what's the difference? Well, I need 11 more, 16 more, and 21 more, and then this would be described as the sequence that goes up in 5s. And it's 6 more than the 5 times table, so this is 5n plus 6, which implies that the rule must be n squared plus 5n plus 6.